All right. Well, as we begin our look at probabilities, I want to start with the review handout that you had last night for homework. And let's see how we did. Some of these very easy, very straightforward. Others of them a little bit more involved. Starting with number 1, it says if a die with the letters A through F on it were rolled, and I've never seen a die like this before, but if it, you have. Okay, I stand corrected. All right, Scott has seen one of these. If a die with the letters A through F on it were rolled, well, you know what? Y'all played Boggle before?
Yes.
Where there's a whole bunch of different, but usually it's not A, B, C, D, E, F on the same die. Normally there's a whole bunch of different letters on it. But anyway, this die has A through F on it. What's the probability of rolling a vowel? Joshua?
1/3.
1 to 3.
1 to 3.
Right, 1 to 3, because there are 2 vowels, A and E, out of 6 total possibilities. Number 2, if a die is rolled and a coin is flipped, how many different combinations are possible, Lana? 12, because the die represents how many possibilities?
6.
And the coin represents how many possibilities?
2.
And what do we do with the numbers of possibilities?
Multiply.
Multiply them. So there are 12 different combinations possible. Excellent job. Number 3, if 6 differently colored marbles are in a bag, how many different ways or orders could 4 marbles be drawn? Scott, what do we have to do, first of all, to figure this out? We're going to have to use a... Not quite a factorial. A what? A permutation. A permutation of 6, but take 4. In other words, 6p4. Anytime you're asked how many different ways or orders are possible, it's a permutation. Now, if it had been all 6 of them, then it is just 6 factorial, right? 6 takes 6. Just use 6 factorial. As is, we're going to multiply, right, the first 4 numbers here to get how many different orders? 360 orders. Excellent job. All right, so it looks like you're the only one who got that. I see them correcting.
24.
All right, does it?
Multiplied 6 by 4.
Well, okay, but Lana, that would be if there were, let's say there was a 6 of one thing and 4 of another thing. Well, it's not. There's 6 marbles. You pull one out. There were 6 different ways that first marble could go. Now there's still 5 in the bag. You reach in, now there's 5 ways the next one could come out. Now there's 4 in the bag. You reach in, there's 4 ways this one could come out. Reach in the bag, now there's 3 ways that one could come out. Does that make sense? That's why the permutation.
Did you say 360?
360 is our answer, yes sir. All right, number 4. If a die is rolled, what is the probability of rolling a 1 or a 6? Now, anytime we see that word or, Joshua, we need to be thinking addition. We're going to take the probability of rolling a 1 plus the probability of rolling a 6. Now, Joshua, what's the probability of rolling a 1?
1 to 6.
And the probability of rolling a 6?
1 to 6.
So the probability of rolling a 1 or a 6?
2 to 6, which equals 1 to 3.
2 to 6 or reduces down 1 to 3, our probability. Excellent. Number 5, if a die is rolled, what's the probability of rolling a 3 or an even number? Now, I do want to point out there's overlap here. There's no overlap here. These are mutually exclusive. If you have a 3, that cannot also be even, correct? Because 3 is odd. So what we're going to look at here is the probability of a 3 or plus the probability of the even number. Lana, what's the probability of a 3?
1 to 6.
What's the probability of an even number?
3 to 6.
So what's the probability of either a 3 or an even number?
4 to 6 or 2 to 3.
Excellent. 4 to 6 or 2 to 3. There's no overlap, which is what we looked at yesterday, remember, where we have to subtract the both. There wasn't a probability of both, because a 3 can't also be even. But as we look at number 6, excuse me, number 6, what's the probability of rolling an odd or an even number? Well, those are also mutually exclusive. Well, what's the probability of odd, Scott?
36.
What's the probability of even?
36.
So what's the probability of odd or even? 6 to 6 or 1. In other words, every number you roll, of course it's going to be one of those, right? Come on, I really hope I get an odd or an even. Yes, I got an even. Or, yes, I got it. Of course you're going to get one of them. It's 100% probability. Now, number 7 goes into what we talked about yesterday, where there's that overlap. What's the probability of rolling a prime number or an even number? How many prime numbers are on the die, class? 3. What are my 3 prime numbers?
2, 3, and 5.
So that's 3 out of 6, right? And of course, how many even numbers are there, class? 3, 2, 4, and 6, right? So that's a 3 to 6. But there is a little bit of overlap. There's a number that falls into both categories, isn't there?
Oh.
The 2. So we have to subtract the probability of both. Well, obviously, how many numbers fall into both categories? 1. The number 2, right? One of those numbers does. So what's the probability of prime or even, realizing they are not mutually exclusive? There is a little bit of overlap, class.
5 to 6.
5 to 6 should have been our answer. Does that make sense now on number 7? Did anyone get 5 to 6? You caught the overlap. Only Lana this time. Good.
I caught the overlap. I kind of wrong numbers. So.
Okay. Questions on 7. Let's go to number 8. 7 students are in a class. Bob, Bill, Jill, Kelly, Mandy, Susie, and Zach. If a student is picked at random, what is the probability that the student is a boy or has 2 L's in his name? So the first probability, class, is probability of picking a boy. The second probability is the probability of getting
L's.
2 L's, right? Are there any boys with 2 L's?
1.
There is some overlap then, right? These are not mutually exclusive, so we need to subtract the probability of both. Now, first of all, how many boys are in the class here, Joshua?
3.
3 of the
7.
7. So 3 to 7, the ratio of probability of boy. How many students have double L's, Joshua?
3 to 7.
3 to 7 as well, right? Bill, Jill, and Kelly. And how many are both boy and double L?
1.
1, and that would be Bill. So what's the probability of boy or double L?
5 to 7.
5 to 7. Did we get 5 to 7 for number 8? Does it make sense now then? All right. Let's move on to number 9. It says from number 8, what's the probability that the student is a girl or has an A in his name? Again, using his as the generic gender there. But girl is the first probability. Probability of an A somewhere in the name, and probability of both. Well, are there any girls with A's in the name that we need to even worry about?
Yeah.
Okay, there is. Okay. All right, so how many girls do we have here, Lana?
4.
Out of
7.
7. How many names have A's in them?
2.
2, Zach and Mandy, right? So 2 out of 7. How many have both A and girl?
1.
1, and that would be Mandy there, right? And so what's the probability of a girl or a student with an A in the name?
5 to 7.
5 to 7, our probability once again. How many have this for number 9? All right. And then number 10, we're looking for the probability of, from question number 8 again, of course. What's the probability the student has an O or a U in his name? O or U? And of course, we should ask ourselves, is there anyone with both O and U, class?
No.
Nobody has O and U. Okay, so that means these are then considered class mutually exclusive. How many have O's?
1.
1 to 7. U's?
1 to 7.
So the probability is
2 to 7.
2 to 7. Questions on the handout? Any question at all? All right. We'll go ahead and set that aside. If you would, turn in your textbooks to page 389. And we are ready to move forward. We've been doing everything with or. Want to look at and. And I mentioned yesterday the probability of getting something and then also getting something else to follow makes the chances less likely, right? By saying an or, by willing to give yourself an option. Hey, I'll take this or this. For instance, pizza or hot dog, they both sound good. Okay, now it's easier to satisfy. But if you're like, no, I want pizza and then I want ice cream. Well, now you've made the chances of being satisfied more challenging, right? And always makes it harder. And mathematically, to show that, you need to know this. That if you have the probability of A and B, it's equal to the probability of A times the probability of B. So in your textbook there on page 389, write this down. And means we're going to have to multiply the probabilities. To try to get 2 events to both occur, we're going to have to multiply. Now again, in algebra, and means add, right? Bob and Susie, B plus S, right? But in probability, the and indicates you're going to have to multiply probabilities. Now, you'll notice here the heading on page 389 says independent events. That's important. Independent events are those which, well, one event does not affect the other. For instance, remember from the homework we said if we rolled a die and we flipped a coin, does the result of the die in any way affect the result of the coin? No, of course not. But for instance, if I had a jar of candies and Lana reaches in and she pulls out a piece of candy, does that in any way affect what Scott could get? Yes. Yeah. He can't get what she got, right? For instance, if I brought in a box of a dozen donuts, and there's one of those, did any of y'all have that brownie batter filled donut from Dunkin' Donuts? Okay, I stopped by Dunkin' Donuts on Valentine's morning to get a box of donuts because, you know, wife likes them, I like them, kids like them, and I got a couple of the ones with brownie batter filling. Now, I'm not officially endorsing Dunkin' Donuts because they have not sponsored my YouTube channel, but if they did, I would certainly endorse them. But anyway, I love the brownie batter inside. Well, anyway, let's suppose we only had one of those, and I give Lana first choice. Now, I don't know if you like brownie batter or not, but for sake of illustration, let's say you do. You're both sitting there thinking, please don't take the brownie batter, please don't take the brownie batter, please don't take the brownie batter. Because you know if she takes it, now you can't have it, right? So independent events. The first event does not affect the second. That's what we're going to focus on today. Okay, tomorrow we'll begin looking at, well, what if the first event does mess with the second and all that? Kind of like a permutation, right? The 6 marbles. Well, once the orange marble comes out, it can't be the next one drawn, right? We're going to look at those more tomorrow. But for now, we're going to look at independent events. Look at the examples here. Amanda and Brian are flipping coins, right? And Amanda gets to flip the coin, and she might get heads or tails, right? There's a 1 to 2 probability that she gets heads, right? Or a 1 to 2 that she gets tails. Well, then Brian comes along, now he flips the coin. Is his flip in any way affected by what she got? No. No. He could flip either heads or tails as well. He also has a 1 to 2 probability. But if I want to know what is the probability that she gets heads and then he gets tails, we're going to have to multiply, because there are actually, as you see with the little diagram there, 4 different ways they could go. It could be heads, heads. It could be tails, tails. It could be heads, tails. It could be tails, heads. So what's the probability of heads, then tails? 1 out of 4 chance, right? By the way, if we were to flip a coin a third time, let's say we got heads, heads. What's the chances the next one is a heads? 1 to 2. Because every time you flip the coin, it's going to be 1 to 2. Each flip is totally separate from before. For instance, we mentally feel like, all right, Glenn's playing heads or tails. He's flipped 4 heads in a row. First thing you do is inspect the coin to make sure it's not a double-headed coin, right? And you realize, it really isn't. And you kind of feel, is it weighted? You kind of set it on the edge and let go. And if it always falls to the heads, okay, it's a weighted coin. It's weighted on the tails side. He's a cheater. But if it like falls randomly, this is just really strange coincidence. These will flipped 4 heads in a row. So you're like, okay, well, now it's got to be a tails. No, it doesn't. It's still a 1 to 2 chance, right? Every flip is completely independent, assuming he's not using a weighted coin, which would make him a cheater, which in certain communities would be dangerous, right? Like playing with a deck with more than 4 aces, short lifespan, okay? Loaded dice, short lifespan. Suspect dealing methods, short lifespan. But anyway, stay out of Vegas, Glenn. Stay out of Vegas. They're on you already. All right. Anyway, we look at another example. Turn the page 390. Amanda has a jar of marbles with 5 red, 2 blue, 3 yellow. She's going to draw 2 marbles with replacement. Now that's important because, like Lana, if she pulls out the brownie batter donut, and she keeps it, now you guys can't get that one, right? But if she picks it up, looks at it, puts it back, and then we move on, now the odds of Scott picking a donut are the same as they would have been before, except if he's worried about our coronavirus germs, maybe he doesn't take the brownie batter, but he's like, nah, Lana's probably safe, and I really like the brownie batter donut, then he takes it anyway and eats it. But anyway, so here she's going to put the marble back after she draws. What's the probability of drawing a blue marble both times, is what it asks. Well, there are how many blue marbles mentioned in that third line down? 2 of them. Out of how many total? 5, 2, and 3 would make?
7.
5, 2, and 3 makes a total of how many?
8.
10. Right? 5, 2, and 3 adds up to 10. So there's a 2 to 10, or let's reduce it down.
1 to 5.
1 to 5. Right? There's a 1 to 5 probability of blue. Then and also multiply the probability of now drawing another blue. Well, if she puts the blue back, there's still how many blue marbles she could draw?
2.
2 of them. So it's still 2 to 10, or in other words, 1 to 5. So what are the odds she draws blue, then blue? 1 to 25. Now, again, one might argue, well, if she set it on the top and she didn't mix them up, okay, let's assume it's totally randomized. She really did mix them up again, and she didn't keep it in her hand as she mixed them up, right? That's the old trick. But anyway, then it would be a 1 to 25 chance of blue, then blue. Let's say she wanted to draw, let's say probability of red, yellow, or blue, Scott?
Yellow.
Yellow. Okay, probability of yellow, and then red, yellow, or blue, Joshua?
Red.
Red. All right. What's the probability of drawing a yellow marble, class?
3
to 10. All right. What's the probability, assuming she puts whatever marble she draws first back, what's the probability of drawing a red marble, Lana?
5 to 10.
5 to 10, or we could reduce that down to
1 to 2.
1 to 2. What's the probability of her drawing yellow, putting it back, drawing red, class?
3 to 20.
3 to 20. Does that make sense? We're just multiplying it. You know, you might be feeling like, I feel like we've done this before. Yeah, we kind of have. Again, this is just showing you, emphasizing that and implies the multiplication needs to happen. Yes, sir.
So on the last one, like when we were doing the ors, we didn't reduce the second fraction, so we can do it on that.
Well, we didn't reduce before, Joshua, because we were adding and you had to have a common denominator.
Oh, yeah.
But with multiplication, I don't need a common denominator. I want the easiest numbers I can get. Now, if this had been, again, this was a 10, but let's suppose, I don't know how, this would be like a 4 to 9. I could even cancel before I did my multiplication. So yeah, we certainly want to reduce as we multiply here. We look over on the sideboard. And back to our candy box here. The odds of drawing out a cherry cordial and then maple fudge. Now, you'll notice something changes here. Because if you pull out a cherry cordial and eat it, there's not 74 candies anymore, are there? There's 73. So notice this is not independent, is it? So we have 2 to 74 chances of a cherry cordial, which I know could reduce to 1 to 37. We have a 2 to 74 chance of cherry cordial because there's only 2 of them in the entire box of 74. There are 8 maple fudge. And if I already got a cherry cordial before, then there's still all 8 maple fudges left. But now out of 73, notice because of the and, we would multiply together. And notice I did go ahead and reduce there at the end. Do we see how the and shows multiplication? By the way, I know we're not talking about dependent events yet, but look at the one below it. The odds of drawing out a chocolate whip, whatever that is. I think it's whipped chocolate filling inside. It's not actually like, okay, nothing like that. Okay, no violence. Well, there's 2 chocolate whips in the entire box. That's 2 to 74. There are 6 cashew clusters, but that would be 6 out of 73, assuming we already ate the chocolate whip. And now there are 8 chocolate truffles, but that's out of 72, because we've now eaten the cashew cluster and the chocolate whip. So that, I mean, now the odds of that, like just randomly dumping all the candies out, picking them out at random, would be 1 out of 8,103 that would be that way.
Where'd you get the 1?
Did you reduce one?
Everything was reduced. Yeah, so coming over here, the 872, notice, can reduce to a 1 and 9. The 2 and 74 can reduce to get a 1 and 37. And then this 6 can reduce with the 9 to get, let's see, that'd be 2 and 3. And then the 2 could reduce it. There was something else that reduced with, I did it on my calculator, so I cheated, but yeah. Anyway, now I'm second guessing it would actually reduce. So I'll have to work that out when y'all are working something else later, make sure I reduced correctly. But anyway, yeah, reducing, of course, at the end. Okay? Questions on the and concept, though. Now again, those are dependent events. We're focused on independent events. So let's take a look here at example 8.5. Read the bold problem for us, if you would, Scott.
Coupons for free food items were randomly distributed to each of the first 60 people at a county fair. Each person had an equal chance of receiving a coupon for one of the following food items: hot dog, turkey leg, cotton candy, and ice cream. Each person also had an equal chance of receiving a coupon for one of the following rides: Ferris wheel, teacup, and carrots. All
right. So there are 4 different food items you get a coupon for, and 3 different rides you get a coupon for, right? So what's the probability of a turkey leg and the carousel? Well, notice it says the probability of teacup and carousel, just use T and C because they're lazy, I like it, is the probability of teacup times probability of carousel. Or not teacup, but a turkey leg. And, well, what's the probability of turkey leg, class?
1 to 4.
1 to 4. 4 food items. What's the probability of carousel?
1 to
1 to 3. And because it's an and, not an or, we have to multiply them together to get the 1 to 12. Look at part B. What's the probability the first 3 people all receive the coupon for the Ferris wheel? They use W for Ferris wheel. So this is probability of Ferris wheel, then the next person also gets Ferris wheel, then the next person also gets Ferris wheel. Now, technically, once a Ferris wheel coupon has been handed out, there should be one less Ferris wheel coupon they could get. But assuming there's an unlimited number of these coupons, it's just whatever they happen to pull. We're going to say since there are 3 rides, that they get a probability of 1 to 3 on the Ferris wheel, right? And the next person comes, that's another 1 to 3. And the next person comes, that's another 1 to 3. Maybe it works this way. Maybe they have a coupon and there's a person who has a stamp and they just randomly pick in and pull out a stamp and they stamp Ferris wheel, put it back in. Next person comes in, it happens to be the Ferris wheel stamp again. Shuffle it back in, happens to get Ferris wheel stamped again. Maybe it's something like that as opposed to printed where the number could diminish. If it's a stamp, that could produce unlimited copies. So we're going to help the book out a little bit here and clarify why it's still 1 to 3 because there's 3 stamps that could be pulled out of the drawer. Got it. Anyway, what's the probability 3 people in a row all get Ferris wheel? Well, notice 1 to 3 times, because it said and, 1 to 3 times, because it said and 1 to 3, gives us 1 to 27. Make sense? And look at probability C. What's the probability the first person did not get a coupon for either ice cream or the teacup? So no ice cream and no teacup. Now it said or, poor choice of words, didn't get a coupon for ice cream and also did not get teacup ride. So they said or, they should have said and. Okay? Or we would have had to do what, class? Add them. But it said and, it should have said and. So we should have multiplied these here. Well, not ice cream is the complement of ice cream. Ice cream would be 1 to 4. What's not ice cream? 3 to 4. Notice not teacup. Well, teacup's 1 to 3, so not teacup, 2 to 3. So what's the probability they come out of here and it does not say ice cream and it also does not have teacup on it? We have to multiply. Notice we could reduce here. The 3's could cancel. The 2 and 4 could cancel to get 1 and 2, and it reduces to 1 to 2. Or you could just multiply, get 6 to 12, and then reduce it to 1 to 2. Questions on the and concept. Probability of this being true and this other thing also being true. Questions? All right, let's take a look at some different things. Looking at numbers 1 through 4, let's just talk these through instead of writing them down because I'm lazy. How would we write the probability of right and left in that order, Joshua?
P parentheses A and B. Oh wait, is it P?
Well, number 1. Probability of right and left. For
Oh.
instance, that one person goes right and the very next person goes left.
P parentheses right and left.
That's what's on number 1. How would I write that out? Lana, help him out.
P right times P left.
Right, probability of right times probability of left, because and means multiply. Okay, so Scott, probability of orange and green. Okay, PO times PG, or P orange times P green if you wanted to write it all the way out. All right, what's the probability that 3 people come in and are asked to place an order for something? The first person comes into the shop and orders a pair of shoes. The next person who walks in places an order for a hat. They could have placed another order for shoes if they wanted. The next person comes in and places an order for a belt. What's the probability of shoe and then hat and then belt? Joshua?
P shoe plus P hat plus P belt.
And?
Wait, and multiply.
So try it again.
P shoe times P hat times P belt.
There we go. P shoe times P hat times P belt. And then that if 3 people come into an appliance store and put in orders, that the first person orders an oven, the next person orders a dishwasher, the next person orders a freezer.
P oven times P dishwasher times P freezer.
There we go. P oven times P dishwasher times P freezer. Questions on those? All right. If I were writing them, I would abbreviate like O and G for orange and green. If I'm saying them, I really don't care. And again, this assumes independent events. All right. Let's take a look at number 5. Back to Amanda's jar of marbles. There are 3 yellow, 5 green. Oh, this is different. 3 yellow, 5 green, and 2 purple. So Mardi Gras colors for no apparent reason. We do not endorse Mardi Gras here at Grace Christian School, just for the record. Anyway, 2 marbles are randomly drawn from the jar, and I wouldn't even if they endorsed me. And the first, they wouldn't endorse my YouTube channel. And the first is replaced before the second is drawn. At your seats, what is the probability of drawing a purple marble out, putting it back, and then pulling out a green marble? At your seats. Probability of purple, then green. Purple, then green. And what do we get, class?
1 to 10.
1 to 10.
Oh.
Should have had a 2 to 10 chance of purple, 5 to 10 chance of green, or in other words, 1 to 5 chance of purple, 1 to 2 chance of green, multiply to get 1 to 10.
I didn't reduce.
Did you have 10 to 100?
Yeah.
Okay, yeah, just reduce it down to 1 to 10. All right, Lana, what did you have?
Oh,
Did you have 7 to 10?
like I tried to before I multiplied, I reduced 10, 10 divided by 5 to 5. I think I reduced wrong. Or
Okay, does it make sense what you should have done?
Yeah.
All right, let's try the next one, letter B. Pulling out a yellow marble, then a purple marble. Yellow, then purple, with replacement. So pull out yellow, put it back, then draw out purple. Do part C. Do part C. Oh, coming there, Joshua. Did you get it? All right, do part C. Yellow, then green, then purple. What's the probability of yellow, class?
3 to 10.
What's the probability of then pulling out a green marble with replacement?
1 to
1 to 2, 5 out of 10, right? What's the probability of pulling out a purple marble with replacement?
5.
2 out of 10, or 1 to 5. So we just multiply. 3 times 1 times 1 is 3, and 10 times 2 times 5 is? So there's a 3 to 100 chance that in that order, yellow, then green, then purple with replacement each time. That make sense? All right, move on to number 6. Each of the 5 letters of the word tooth are written on a separate paper and placed into a hat. 2 letters are randomly drawn from the hat, one after the other, replacing the first before the second draw. What is the probability of drawing a T, then an O? What is the probability of drawing a T, then drawing an O? Scott's got it. Lana's got it. And Joshua, what do you got?
4 to 25.
Good, 4 to 25. Each is a 2 to 5 probability. Multiply them to get to 4 to 25. How about a consonant, then a vowel? Consonant and then a vowel. Now, if it's a consonant or a vowel, it's 100%, right? Because everything is a consonant or a vowel. But it says consonant, then vowel. It's not 100% anymore. And Lana's got it. Scott's got it. Joshua's got it. Scott, what do you got?
25.
Good. 3 to 5 chance of consonant, 2 to 5 chance of vowel, multiply to get 6 to 25 chance. Did we get that? All right, letter C. An H, then another H. An H, then another. Oh, then a letter other than H. I can't read. H and then something other than H. I'm sorry. Because you could do two H's if you put the first H back, right? So it's not like, there are two H's. Well, there are if you put it back. No, sorry. An H, then something other than H. Sorry. What do you got here? Lana's fixing it. And Lana, what you got?
2 to 20.
Well, what's the probability of H?
1 to 5.
What's the probability of anything other than H?
4 to 5.
Now multiply to get
4 to 25.
4 to 25. 4 to
I thought
25.
you had to subtract 1 minus 4 to 5.
No, not 1 minus 1. 1 to 5 times 4 to 5.
Oh.
Anything other than H. The example they're looking at there is 1 minus 1 to 5, Lana, which is 4 to 5, right? Something other than H. If H is 1 to 5, then the probability of anything other than H, or the complement of H, is 4 to 5. But then you just multiply. All right, let's move on. Number 7. A bag of tiles contains 1 tile for each letter of the alphabet. On a turn, a player rolls a 6-sided number cube and draws a letter from the bag. Rolls the dice, pulls a letter. What's the probability of getting a Z and rolling a 6? What's the probability of drawing a Z out of the bag and rolling a 6 on the die? How many letters are in the alphabet?
26.
26, good. Okay. So the probability of a Z then is 1 to 26. And, or times, the probability of a 6. Well, what's the probability of a 6?
1 to 6.
1 to 6. So what's the probability of a Z and also rolling a 6?
156.
Good, 1 to 156. 1 out of 156 chance of a Z and a 6. Ooh, this is interesting. What about a vowel and an even number? Probability of vowel and an even roll. Probability of drawing a vowel out of the bag and then rolling on the die some even.
Is that including Y?
Y is not technically a vowel. It's sometimes lumped in with the vowels, but it is not technically a vowel. It behaves as a vowel. So that leaves how many vowels, class?
5.
5 to 26, right? What about the even number?
3 to 26.
Ooh, careful, even number?
1 to 2 on the die.
3 to 6, it's on a die. There's
Yeah.
6 numbers on the die, 3 of them are even, so 3 to 6, or 1 to 2, right, we could say. So what are the odds of pulling a vowel and rolling an even number?
15 to 156.
Well, we could, but if you reduce to 1 to 2 first, rather than 3 to 6, it makes it easier, 5 to 52. And now you don't have to reduce. 15 to 156 would reduce to this anyway. But I don't like reducing big numbers. All right, here's another one for you. What's the probability of drawing a consonant and not rolling a 1? The probability of a consonant and not a 1. Is it consonant or consonant? Consonant. Probability of consonant and not a 1. I just don't want a 1. And come on, please, not a vowel. You could say probability of not vowel and not 1. And use cross cancellation to make it much, much easier. Big fan of cross canceling. Scott got it? Hayden can't wait for this class next year. He's already, he's like, man, I can't wait to take pre-algebra. I know.
Well, and also
Danielle's dreading this class, just for the record. She doesn't know anything about it, but she's dreading it. But Hayden's like, man, I can't wait. All right, did we get 35 to 52 for our probability? 21 to 26 of a consonant, 5 to 6 chance of not getting a 1, and then cancel the 6 with the 21 to get 7 and 2, makes our multiplication a little easier. Let's move on to number 8. A spinner below is spun twice. What's the probability of spinning red and red? What's the probability of red and red? Lana?
1 to 36.
Good, 1 to 36. Both red is 1 to 6 each time. Again, no reason you can't spin back to back red. It's not like once you spin a red, it's off the table. So 1 to 6, 1 to 6, 1 to 36. For the next one, what's the probability of spinning blue and blue? And again, if this sounds familiar, we did problems like this quite a bit, didn't we? So it's really just more of the same. Well, what's the probability of blue, class?
1 to 2.
3 to 6 or 1 to 2 both times. So the probability of blue and then another blue.
1 to 4.
1 to 4. 1 to 4, right? 9 to 36 or 1 to 4. What's the probability of white then blue? White then blue. And are we good to go on this? If there's 2 white areas out of 6, that's a 2 to 6 chance of white. Reduce that down to 1 to 3. If there are 3 blue areas out of 6, that reduces down to 1 to 2. And since we've got and, not or, multiply, then we get a 1 to 6 chance. 1 to 6 chance. Questions, Joshua? All right, turn the page. Number 9. A deck of cards has 1 card for each of the numbers 1 to 10. So we've basically set aside everything else. Maybe we just took 1 suit, ace through 10. If the first card is replaced and the cards are shuffled, what's the probability of drawing a 1, mixing it back in, or an ace, mixing it back in, reshuffling, and then pulling out a 10? Got a deck of cards, number 1 through 10. What's the probability of drawing an ace, then drawing a 10 after replacing the first card, which we presume to be the ace in our illustration? Lana?
1 to 100.
1 to 100. Good. What's the probability of drawing a 5, putting it back, then drawing another 5? That's what magicians do. What is your card? It is the 5 of diamonds. All right, I'll place it into the deck and shuffle a little bit, and voila, it's still the 5 of diamonds. Nice cut.
I don't know how to do that.
Yeah, then stick the thumb in just a little bit, hold the spot. Yeah, I can do it sometimes if I'm good. I don't practice a lot, but you know, every now and then it comes in handy when playing card games. Hey, I'm honest though. After I cheat and win, I always tell my wife, "Well, I have to confess, I cheated. I did this," and then she hits me and doesn't want to play anymore. But at least I tell her, you know. Anyway, what's the probability of 5 and 5, class?
1 to 100.
100 again, of course. What about an odd number and then a 3? Probability of odd, then 3. Now again, or you would say these are not mutually exclusive, right? But it doesn't matter if they are or not because it's odd, putting it back, and then 3. So, watch these. Good to go, good to go, and good to go. Excellent. Take a look at the next one, number 10. On each turn of the game, 2 6-sided number cubes are rolled. We call them dice. One is red and one is white. What is the probability of rolling a 3 on both cubes? What's the probability of rolling a 3 on both cubes? Class?
1 to 36.
1 to 36, right? The 3 is 1 to 6, the other 3 is 1 to 6. That's 1 to 36 that you would get a 3 on both cubes. All right, what about this? an even number on the red cube and an odd number on the white cube. Even on red, odd on white. I don't have red chalk, so we'll do yellow and white on the board. What's the probability of an even number on the red class? 1 to 2, 3 to 6, or 1 to 2. And what about odd on the white? So what's the probability of an even on the red and odd on the white?
1 to 4.
1 to 4 probability. What about an odd number on the white and a 3 on the red? Odd on the white and 3 on the red. Good to go. And good to go. All right, look across the page. You're going to work these on your own now. I want you to do numbers 3 through 6. Now, again, we're not going to do the decimals and the percents and stuff like that. We're just going to go with the ratios. But number 3, 4, 5, and 6 on page 393. About 6 minutes to work these problems, and then we'll take a look at the answers together. about a minute or so to be finishing up. For sake of time, let's see how we did. Anyone able to finish 3, 4, 5, and 6? All right, Lana, how far did you get?
Well, I finished 4, 5, and 6, but 3 was a
3 threw you off. All right,
Yeah.
and Joshua?
I was on number 5.
We're on number 5. All right, let's go and take a look at this. Number 3, the last 2 questions on a quiz were true or false questions and a multiple choice question with 4 answer choices. Each question had only 1 right answer. What's the probability of guessing both questions correctly? Well, for the true or false, to get that one right, there's a 1 to 2 chance of getting it right. And on the multiple choice, there's a 1 to 4. What's the probability of getting both of them right? That'd be 1 to 8 probability.
I had that at first, but then I changed.
All right. What's the probability of getting both wrong? Well, there's a 1 to 2 chance you get this one wrong. But there's a 3 to 4 chance you get this one wrong, right? So that's really a 3 to 8 chance you get both wrong. And what are the odds that both correctly from the remaining options, knowing that A and B on the multiple choice were incorrect? Oh, okay. So true or false, it's still a 1 to 2 chance. But if you're told up front, A is not right and B is not right, it's either C or D. Well, now you've got a 1 to 2 chance on the multiple choice. You've narrowed down. You know A and B are wrong. It's either C or D. I can't tell which. Well, now it's a 1 to 4 chance of getting them both right. Does that make sense? All right, questions on number 3 at Alani. You say there's some trouble. Does it make sense now?
Yeah.
All right, good. You had trouble as well, but it makes sense now. All right, and you got them. All right, let's take a look at number 4. We got the spinner. What's the probability of getting green area and then a coin is flipped and getting tails? Well, green is 1 to 5, tails is 1 to 2, so that'd be 1 to 10 of green and tails.
Wait.
What?
Yeah, there's
Sorry, 3 to 5. 5 spaces, 3 of them are green. Sorry, 3 to 5, make that 3 to 10.
Yeah.
All right, I'm getting a
That's
weird
what
reaction.
I
I'm
had.
looking at the spinner. Oh, duh, there's 3 greens. All right, 3 to 5 green, 1 to 2 tails, 3 to 10 green and tails. All right, how about even and heads? Well, heads is 1 to 2. There are 2 even numbers, so 2 to 5. Cancel the 2's, 1 to 5. Chance of even and heads. All right, not a 1. Well, there's 4 to 5 not ones, and not tails, in other words, heads, which is still 1 to 2. Reduce, cancel a little bit here to get 2 to 5 of not 1 and not tails. Good to go there. All right, number 5, number cube, with numbers 1 through 6 is rolled twice. What's the probability of 1 and then a 6? Well, that would be 1 to 36. How about even and then odd? Well, even is 1 to 2. They're half of them even, half of them odd. Stay with me. Odd is also 1 to 2. So even then odd would be 1 to 4. And then less than 3. Well, there's only 2 numbers out of 6, or 1 to 3 chance of less than 2. Of less than 3 rather, then a number greater than 3. Well, there are 3 numbers greater than 3, 4, 5, and 6. That's 1 to 2, so 1 to 6 chance of less than 3 and then greater than 3 on consecutive rolls. How do we do on number 5? All right, and then you two did not get a chance to do number 6, or you did?
I did.
You did. Okay, let's take a look at 6 then. Oh, the months of the year again. All right, all the months are written down, 2 papers drawn, replacing before the second draw. That's important. April, then June. Well, April's 1 to 12. June is also 1 to 12, so 1 to 144. April, then June. Month ending in R. How many times have we done this? It's got to be just September, October, November, December. That's 4 to 12. It's 1 to 3 R. Then ending in Y. And I think we said it's January, February, March, April, May, June, July. 4 as well. Okay, so 4 out of 12 are 1 to 3. So 1 to 9, end in R, then end in Y. And then May, and then not May. Okay, May is 1 to 12, not May is 11 to 12. So May, and then anything other than May is 11 to 144. That wasn't quite as bad as I feared. All right, questions on this? All right, we'll look at more with this tomorrow. We'll also get into those events over there where they're not independent. The first affects the second, but I think you kind of already know what you're doing with those. So tomorrow really shouldn't be too hard at all for you. No homework this evening. Have a wonderful rest of your day. And you are dismissed.
No math.